Here we have the question, and it might be a little hard to read, but it's in the document. Do V1 equal the column vector 1117 and V2, the column vector negative 3351, span the vector space R2? Okay, well, let's see what we mean by span. Okay, V1 and V2 are said to span R2 if and only if any vector in R2 is a linear combination of V1 and V2. Well, there are two phrases after the if and only if, are two things here. Any vector in R2 and linear combination of V1 and V2. We need to interpret these phrases mathematically. Okay, well, what do we mean by any vector in R2? Okay, any vector in R2 could be, well, the general vector with variables a and b. The vector column vector ab could be regarded as a vector in R2. The vector xy, the vector x1, x2. Just three examples of how we could write a general vector in R2 without specifying the values of either of the coordinates. Okay, so to interpret this any vector in R2, we need a general vector in R2, and we could use any one of these. I chose AB because that's the first one somebody suggested. Could have easily, as easily used either the XY or the X1, X2, or any of a myriad other possibilities. Okay, now what do we mean by a linear combination of V1 and V2? Well, that's a term that should, by the time we see this, be familiar to you. It simply means a sum of multiples of V1 and V2. So, in words, I would say a sum of multiples of V1 and V2. Okay, but a sum of multiples of V1 and V2 would be written some number times V1 plus some number times V2. I'll use C1 and C2 for those two numbers because we're familiar with that notation. So to say that any vector in R2 is a linear combination of V1 and V2 would be to say that for any vector AB, column vector AB, we can find a sum of multiples, a linear combination, C1 V1 plus C2 V2, which is equal to AB. So that interprets our statement. Now, with this interpretation of our statement, again, I've got some dots here. This statement immediately, if we remember that V1 is the vector 1117 and V2 the vector negative 3351, C1 V1 plus C2 V2 is the vector 11C1 minus 33C1, 17C1, oh, good heavens, plus 51C2, and that should be 17, well, that should be 11C1 minus 33C2. Okay, that should be a C2 there. Anyhow, we get this. Okay, if we do a C1 times this vector plus C2 times this vector, add the two vectors, this is what we get, and that has to equal the column vector AB, meaning that 11C1 minus, well, I'm sorry, I was about to say what you get for simultaneous equations, and we could get simultaneous equations. This equals A, this equals B. That gives us two simultaneous equations that we can solve. But the simultaneous equations, or this equation here, lead to the matrix equation, where we have the vector with columns 11, 17, negative 33, 51 multiplied by the constants C1 and C2 equals AB. Now, the question is, can we always find a C1 and C2 for any given AB? Because then, if we can always find C1 and C2 no matter what A and B is, it follows that any vector in R2 can be written as a linear combination of V1 and V2, so that V1 and V2 do in fact span R2, which consists of all vectors of the form column vector AB. Okay, well, matrix equation. And again, we should be very familiar with this now. To solve this matrix equation, all we have to do is find the inverse of this matrix, multiply both sides by the inverse, and we get C1, C2. Now, we don't actually have to do that if we can just establish that this matrix has an inverse, because if it does, we can do that and we can find our C1, C2 for any A and B. Okay, well, again, for these, for these vectors, for this equation is solvable if and only if then this matrix is invertible, which happens if and only if the determinant of the matrix is non-zero, and that is so. You can multiply these out. This product, the diagonal product, is positive. The product on the other diagonal is negative. Since we're subtracting the product on the second diagonal from the product on the first, we're going to have two positives. So we're clearly not going to be able to get zero. We can't add a positive. We can't subtract a negative from a positive and get zero. Okay, so the conclusion then is that these vectors do span R2. Okay, now if the vectors had been 11, 17, and 33, 51, then everything would have been the same, except the matrix would have been 11, 17, 33, 51. Well, in that case, and you can verify it, 11 times 51 is equal to 33 times 17. And that's true because when I made these up, I just multiplied this matrix, or this column vector, by 3. So 11 times 3 is 33, 3 times 17 is 51. Okay, in this case, this product and this product turn out to be the same. You can think about why that's assured if this vector is a multiple of this, and the determinant is 0. In this case, the vectors would not span R2. These two vectors don't span R2. And I'll say a little more. These vectors, this one being a multiple of this one, look like this. One is 3 times as long as the other, but they lie on the same line, so that when you add two of them, you're always going to get a vector that lies on that line. Whereas here, the two vectors are not in the same direction. Okay, they might be like this, where they don't lie on the same line, so that you could get any vector in R2 from multiples of these two vectors, as we've seen by previous constructions. Okay, so in any case, here's your test. Okay, and basically test comes down to put the vectors, make the vectors into the columns of a matrix, and see if the matrix is invertible. Now, sometimes you have maybe you have 3 vectors in R2, and you can't talk about invertibility of the matrix. Then you have to talk about reducing the matrix. If the matrix doesn't reduce properly, you don't have, the vectors don't span the space. But that's a technique you'll understand when you see it. Okay? So, again, this, and by this, I mean this up here, is what occurs for two vectors in R2 if and only if one of the vectors is a multiple of the other. And that would be a good thing for you to prove. And to prove that, you'd have to prove that if one vector is a multiple of the other, then this is going to occur, meaning you're going to get a determinant 0. And conversely, if you get a determinant 0, that means that one of these vectors is a multiple of the other. So, useful thing to prove. Everybody should by now be able to prove this statement.